The Big Bang is a theory on how the universe started, and is the most commonly accepted theory by modern science. It is believed that before the Big Bang happened, all of matter in the universe was contained within a single point, which then expanded out. This theory was envisioned by Edwin Hubble in the late 1920s. He discovered that all of the other galaxies in the observable universe were expanding away from ours. This meant that there must have been a point in time when all the matter in the universe was contained within a single point. In a violent event, likened to an explosion, all of the matter and energy expanded in all directions. The matter soon formed into atoms, paving way for other structures to be created. Stars and planets were then formed. Today, the universe is still expanding at an exponential rate, meaning that it is accelerating. The way that Hubble worked all this out was with redshift, the Doppler effect, and the color spectrum. The Doppler effect is used in describing waves with moving sources. As the source moves, the waves behind the source become stretched, making the waves longer. This is called redshift, and it applies to light waves as well. As the light travels, the source moves away and the light waves are stretched. Longer light waves are close to red on the color spectrum, while shorter light waves are blue. Hubble worked out that if galaxies viewed through a telescope are more redshifted than other sources of the same reaction, which is burning hydrogen, the universe must be expanding. From this he knew that other galaxies in the universe must be expanding. There must have been a point in time when all that exists within the universe must have been contained within a single small point. Another piece of evidence for the Big Bang is cosmic background radiation. Shortly after the Big Bang, the universe was very hot, and all of matter in the universe was in a sea of tightly packed matter. The thermal energy was absorbed by the quark matter, making the universe an opaque white sea. As the universe expanded, the matter was able to spread out, as well as the thermal energy. The Big Bang Theory predicts not only does it exist, but also that it is visible as cosmic background radiation. The thermal energy still permeates the universe, but because it can no longer be absorbed by quarks, it is transparent. It is, however, still observable by radio telescopes. There were various missions made to study cosmic background radiation. Two noteworthy missions are the Cosmic Background Explorer, or COBE, and the Wilkinson Microwave Anisotropy Probe, known as WMAP. COBE was able to map variations of background radiation in the early universe, with WMAP providing similar results in an updated resolution. The variations were very small, within a few microdegrees. This means that the CBR of the universe is very uniform, despite its size. The final major piece of evidence for the Big Bang Theory is the mixture of elements that is present within primordial stars. Because light takes so long to travel across the universe, the light that we see from distant stars is actually very old. This means that when we look at one of these stars, we can see what elements were in the universe shortly after it was created. The Big Bang Theory states that the universe would have been filled with hydrogen, helium, and lithium ions. The emission spectrum from these stars shows that these stars are made from these elements. This means that these elements were in the early universe.
Stars begin as massive dust clouds, called stellar nebulae. An example of a stellar nebula is the Orion Nebula, which is visible from Earth. Because there is so much gas in these bodies, gravity causes them to compress and start spinning. This causes the center of the nebula to become very hot and dense, often causing nuclear fusion. When this happens, the gas starts to burn, creating a protostar, which is believed to be similar to a star core. Gas is sucked into the star, while quick and sudden bursts of light are released as remaining particles are blown away. This protostar will eventually change into a star. A typical star created with this method will last around 10 billion years.
From here, a star takes two different paths based on its size. The first path is becoming an average star. Average stars are similar to our Sun. They are large balls of gas that emit large amounts of light and attract planets and other bodies into their gravitational field. Apart from their birth and death, stars don't change a lot during their lifespan. An average star will then turn into a red giant when it exhausts all of its fuel. It will expand, destroying all of the planets and other bodies within its gravitational reach. Some red giants have reached up to 1 billion kilometers in diameter. After all of the fuel has been burnt, the nuclear fusion will cease, causing the star to collapse on its.
The red giant then forms a planetary nebula. These nebulae are named so because they look similar to planets when viewed through traditional telescopes. The giant releases shells of burning gas, which expand outward. The remains of the star core will become a white dwarf, similar to Sirius B, which has the mass of the star compressed to the size of the Earth. They are prevented from collapsing further by the pressure created by dense electrons. These small stars may contain the mass of a star, but they are very dim and faint.
The second path that a star can take is to become a massive star. Stars such as VX Sagittarii are described as massive stars. They must be at least 8 times the size of our Sun to be called massive stars. While these stars may be larger, they tend to burn their fuel quicker. Once they have burnt their fuel, they turn into a red supergiant. These giants are similar to normal red giants, but they instead create supernovae. A supernova is caused when a red supergiant runs out of fuel to burn. It is a bright explosion that can outshine a galaxy for a few days. What is left is one of two things. The first is a neutron star. These objects are roughly 20 to 30 kilometers wide, but contain twice the mass of our Sun. The alternative is a black hole. When a core is massive enough, at least 2.5 times the mass of the Sun, its collapse can crush atoms, creating a singularity. These objects are small, but their gravity is so strong that nothing can escape, not even light. This means that the singularity and the area around it is black, which is why they are named black holes. There aren't many known black holes, but it is believed that there is one at the center of the Milky Way.
The Milky Way is a dark spiral galaxy that has existed for 13.6 billion years. It is significant to us because it houses our planet and solar system. It spans 100 light years and consists of 200 billion stars, as well as some planets and dust. There are two major arms in the spiral shape of the universe, the Perseus arm and Scutum Centaurus arm, as well as two minor arms, the Carinus Sagittarius arm and the outer arm. There are also various smaller arms, called spurs. In one of these spurs, the local arm, is our Sun and solar system. It is difficult to note the true size and shape of the universe, because we cannot view it from the outside. Modern science can only make educated guesses based on the positions of nearby stars with Hubble telescope pictures. At the center of the Milky Way is a large black hole, called the galactic bulge. It is difficult to see, because the black hole sucks a large amount of dust and gas clouds, which causes the black hole to be covered. It is believed to be the remains of a massive sun that ran out of hydrogen to burn, causing a supernova. This compressed the mass of the star into a black hole, spanning roughly 22.5 million kilometers. From this, our galaxy formed. Another galaxy similar to ours is the Andromeda Galaxy. It is a large spiral galaxy that is close to the Milky Way, approximately 2.5 million light-years away. It contains 1 trillion stars and has 400 billion solar masses. Viewing this galaxy is also difficult, because the light coming from it is distorted by the gravity of nearby galaxies. While the Andromeda Galaxy has more stars than the Milky Way, scientists believe that our galaxy has more dark matter, which is undetectable by telescopes, so the Milky Way may be larger. It is believed that in 4.5 billion years, the Andromeda Galaxy will collide with the Milky Way, causing a new elliptical galaxy to be created, called Milpromeda. From Earth, the night sky will light up as new stars are created, but because of the distance between the stars in our galaxy, our solar system will likely be intact.
The Sun and Moon are the two most visible objects from Earth and have major effects on our planet. The Sun is the star of our solar system and is responsible for almost all of the energy on Earth. It also holds our solar system intact by keeping planets and other objects within its gravitational pull. The Sun makes its energy by fusing hydrogen into helium. While many people liken the Sun to a burning ball, the energy produced by its nuclear fusion is too intense to be created by combustion. This energy contains both light and thermal energy, which takes about 8 minutes to travel to our planet. Like many other stars in the Milky Way, the Sun is a yellow dwarf star, with a surface temperature of around 5,800 degrees Kelvin. It has a diameter of 1.4 million kilometers and is 333,000 times more massive than the Earth. It rotates, similar to Earth, taking between 25 to 36 days to complete a full rotation. The Sun has various layers with different temperatures. At the center, energy is created by fusing hydrogen into helium. This is called the core. The energy then travels through the rest of the interior to the surface that we can see, called the photosphere. Outside of this is the Sun's atmosphere, consisting of the inner chromosphere and the outer corona. From this atmosphere, solar flares are released. These are caused by disturbances in magnetic fields. The result of this is a massive release of radiation and light. The strongest recorded solar flare happened on the 4th of November 2003. Worldwide blackouts in radio communication and satellite functionality were caused as a result of this. The Moon, on the other hand, is a natural satellite of the Earth. It is a nearly spherical, rocky body, about a quarter of the Earth's size with 80 times less mass, making it the most massive moon in the solar system. It is believed to have formed from a large object, about the size of Mars, colliding with Earth. Mantle was broken off from both bodies, which fell into Earth's gravitational pull. These fragments eventually clumped together, which formed the Moon. This collision also tilted Earth off axis, giving us our 4 seasons. The Moon also has a gravitational effect on our oceans. The surface of the oceans are pushed and pulled based on the position of the Moon. This is called tidal force. When the Moon is visible at night, we only see one side. This is caused by the reflection of light from Sun. However, only certain parts of the Moon will be lit at certain times. These are called the phases and are regular, with a cycle lasting about 28 days. The first photographs taken of the opposite side of Moon were taken by the Soviet mission Luna 3. The first moon landing by humans was by Lance Armstrong, Buzz Aldrin and Michael Collins of the Apollo 8 mission in 1968.
Life on Earth has a long and detailed past. It has taken 7 million years to evolve the species we now know today. 4.5 billion years ago, the Earth was just being formed. It was under constant bombardment from asteroids, making the surface an ocean of hot lava. The air in the atmosphere was also completely unbreathable. 500 million years later, when the surface finally became habitable. At this point, there was only single-cell life forms, such as RNA-based bacteria, that likely existed in early forms of the ocean. This was around 3.8 million years ago. It was about 2.15 billion years ago when bacteria with photosynthesis existed. This paves the way for the first plant cells to evolve. 150 million years later, the first cells with internal organs evolved. This is believed to have happened when 2 cells engulf each other and begin to live symbiotically. 500 million years later, these cells divide into the early forms of plant, animal and fungi cells. These cells will become more distinct with the development of multi-cell organisms within the next 600 million years. It is unclear why this happened, but it is believed that these early life forms formed something similar to bacteria colonies. In the next 800 million, life continues to develop. The underwater life forms develop into the first fish, which later evolve into early reptiles and other land-based animals, which could move under their own power. Plants such as grass and some early wood-based plants also began colonizing the surface. Eventually, early primates gave way to gibbons, orangutans, gorillas and, lastly, early humans. The first sign of early humans was early monkeys being able to walk on 2 legs and begin eating meat. This was about 3.5 million years from the present day, and it was about 500,000 years after this when the first stone tools were being used. This was the first time that a life form on Earth had used some form of technology. About 1.5 million years later, primitive humans were using fire. This allowed for cooking food, which led to better health, as well as warmth and light, when the sun went down for more night activity. The use of stone tools was also becoming more complex, with carved grips and blades being invented. Finally, about 200,000 years ago, the first Homo sapiens evolved, and that is as far as advanced life has evolved.